Alright, let's try to find some simple example to try the application of Castigliano theorem. So the first example we're going to consider is two bars with cross-sectional area A1, A2, and the length L1, modular elasticity E1, L2, E2, and this is the wall. And there is a force applied to here and in the middle, right? So you have a rigid plate, and in order to keep the symmetry, you have a rigid plate, so you apply P over 2 here and P over 2 here. This is rigid plate. Now we want to find deformation at different points. So for example, if this is A and B, these 2 points here, we want to find delta A, delta B. And we want to solve this using Castigliano theorem, right? So the first thing I need is the Castigliano theorem. It says that the derivative of internal energy with respect to a force like P acting at a point that P is acting is the deflection at that point that P is acting. So here we have force P here, right, in the middle. So all I need to do is to find the internal energy and then take derivative, and that's my deflection. So if you refer to the tables of the formula for internal energy, which will be given to you, you will find a relation like, let me find it one more time because I forgot it. So for a spring, the internal energy is Fq over 2k, take the derivative, this is respect to F, like that. So that's for just simple spring. But if you take derivative with respect to F, it's going to give you the spring constant formula, right? And the spring constant for the bar is sigma is equal to E epsilon sigma A over F over A E delta L over L. So F is equal to A E over L delta L. So that's K. So if you put it here, UI is equal to force 2 times K, and K is equal to AE over L. So that's going to give you L F squared 2AE. That's the internal energy for each bar. Now, the internal energy, this is the total internal energy for the entire system. So the internal energy of 2 bars, UI total, is UI1, this bar 1, plus UI2. UI1, according to this formula, is equal to L1 P square over 2 A1 E1. The length of that bar, force in that bar. So if you draw force diagram, axial force diagram, here force is 0 because it's after this ball. There is no axial force here, but the force here is P, right? So you get P, the force in unit 1 is P. So L1 P So P over 2 is P. P square over 2 A1 E1. That's the internal energy of bar 1. Plus internal energy of bar 2, which is we use the same formula. L2 force in bar 2. So now force in bar 2, as we thought, is just 0. Because if you cut it, let's use a different color. If you cut it somewhere here, right, and then you make a free body diagram of that part, there is nothing here. So the axial force is 0, right? P is acting in the middle, not on the tip. So that's going to be 0 squared over 2A2 E2. The reason that I wrote it is because I want you guys to learn it, because this is just 0. You can just ignore it, right? But there is something here, it's just 0. Now if this P was acting at the tip, there would be a P in both 2 and 1. Okay? So the entire total energy is this. Now, what's the deflection at point A? The deflection at point A is partial UI total, which is this with respect to P. Okay? So what is this? Derivative of this with respect to P is 2P to power 1. The rest is just constant. This is constant because P is variable with partial P, right? So that's going to be 2P L1 to A1 E1. 2 cancel out with 2, and you get P L1 A1 E1. So the deflection at this point is P L1 A1 E1. Now the question is, find the deflection at point B. Deflection at point B. So again, I say I should actually, in order to find the deflection at point B, you can put a force like P2, right? This is not P, P2. Put the force there, and then write the internal energy of the system. So in that case, the internal energy would be a function of P and P2 and the modulo of elasticity and length of both sides, like this. And then take derivative with respect to P2, but at the end, put P2 is equal to 0, because there was nothing here. We just added to the system. So this is just one example of how we find deflection using energy method, which is the Castigliano, which is the particular conclusion of energy method. One way to do in energy method. So the next example, we're going to solve a beam, and after that we're going to solve, we're going to talk about the homeworks and how we can solve some of the hard problems in homeworks.